Hello everyone, my name is Heo Wen, and today I will be doing a presentation based on my MP complete problem for Project 6 in Artificial Intelligence. So the problem I chose to solve was called Longest Path Problem. It's very similar to the TSP problem or the shortest path problem, except for instead of trying to minimize the total cost for traveling a simple path, we are trying to maximize the cost for traveling that path. And a simple path, as you notice from the picture, is just a path that connects every single node, right, without repeating any previous nodes. And some of the applications for optimizing the solution to this problem is critical path, which is very relevant in project management, where you're trying to get a project within a certain deadline or within a certain time frame. So you can run this algorithm and try to find the shortest time possible to complete the project. And based on that critical path, you are able to determine a window for, if the project is doable or if it will meet deadline or not. Another application is any maximizing problem or maximization problem, where instead of trying to minimize, you're trying to maximize. For example, the edges might represent profit for a certain company if they take a certain route. So this algorithm would try to maximize the total path and therefore maximize the profit. Another one is computer networking, and then social network mapping. Here I'm going to discuss the approach that I took to solving this problem. You might not be surprised, but it shares a lot of logic with the previous project, Project 5. The only difference is going to be in the fitness function. In Project 5, where we solved TSP, the fitness function was defined as the shorter the path, the more fit it is. Here, it's going to be the inverse. The longer the path, the more fit it is. And so in the GA, the following steps or operations have to be implemented in order for the algorithm to work. It's order and numbered, population initialization, fitness evaluation and selecting the parents, crossover, mutation, the discard step, and the terminating condition. Let's start with population initialization. So the initial population is randomly generated, meaning each chromosome, which is an order list of nodes. For example, a chromosome 1, is a set consisting of 1, 2, 3, 4, represents a path through node 1, 2, 3, and ends at 4. So in our case, if we had a graph consisting of 100 nodes, well, the chromosome will now have the size of each chromosome will be 100, and each chromosome would be randomly generated, meaning it selects different nodes randomly and then place them in order. And then a couple constraints have to be followed when generating the population. The length of the chromosome should never change. So because we're trying to visit every node at least once, so that should not alter the length of the chromosome. The size of the population should also not change. Next up, we have fitness evaluation and parent selection. As I discussed before, fitness is going to be the total path distance, which is the cost of visiting every single node at least once. This is basically computed by summing up all the edges. Here, as I stated before, the longer the path, the more fit it is. But in TSP, the shorter the path, the more fit. So just for comparison purposes, after the fitness for each chromosome has been evaluated and assigned, we move on to parent selection. This is done using a roulette wheel selection. So the percentage of the wheel that a chromosome occupies is equivalent to its fitness divided by the total fitness of the population. And then, as you can imagine, if a chromosome is more fit, it's going to occupy a bigger portion of the wheel. hence it's going to have a greater probability of being selected for reproduction. And this is how we're going to get our optimization. And each time we are selecting 2 parents. Next up we have crossover. Crossover occurs between 2 chromosomes, or 2 parent chromosomes, and it generates 2 new offsprings. And the hope is that each time we're creating new offsprings that it's an improvement over the previous or their parents. And below we have our crossover method defined. It takes 2 parameters, parent 1 and parent 2. We start out by initializing a empty array of unique points. I could have named that better. It basically contains a list of genes or gene indexes that we're going to perform crossover. And so for up to the number of points allowed, which is a constant we define, it could be 3, it could be 10, it could be any random arbitrary value, as long as it's less than the length of the chromosome. But we try to keep it at a optimal or ideal value, so we don't want to be crossing over too many points or too little points. But for each one of those points allowed, we are selecting a random gene in the chromosome and adding it to unique points. And after we have selected all the unique points, we iterate through each point and then exchange that specific gene between the 2 parents. And at the end, we return 2 new offspring. And to add a probability or to control the rate at which crossover will occur, we initialize a variable called PD, and we typically keep it at 0.07. Next up we have mutation. Mutation ensures that the GA is not stuck at local optimum and that the population maintains an adequate diversity. Here's our mutation method. First we select a random chromosome, which is our candidate, and then we select 2 different genes to perform mutation. And then once we have those 2 genes, we perform a swap. So for example, if it was if the chromosome was 1, 2, 3, or 1, 2, 3, 4, and we chose chromosome 1 and 4, then the index of chromosome 2 will be populated by 4, and then the index of gene 4 will be populated by 2. So that's a swap. And then the rate at which mutation occurs is controlled by PD. And generally we try to keep this pretty low at typically around 0.001. And then the next and close to the final step is the discard step. And so whenever we're adding new offspring to the population, we are also ensuring that the population size does not change. So we have to remove so-called bad chromosomes. And so this is performed by first sorting the population based on their fitness. So the first chromosome in the order list will be the worst fit, and then we select the number of the amount of chromosome we will remove is going to be the same as the number of chromosomes or offspring that we're going to be adding into the population. So we're taking out as much as we're putting in, and that's how we're going to ensure the population size does not change. And then for each one of those candidates, we remove it from the population. Next up, we have the terminating condition. So this will basically prevent the GA from running indefinitely. And in our case, it is controlled by a constant called max generation number. What that means is basically we are allotting a fixed number of generations that are allowed to be generated before it terminates. So as you see in the pseudocode below, there's a while loop, and it's checking each time what is the current generation. If it's less than the max generation allowed, we keep evolving the population, and each time we evolve, we increment the current generation number. And once the current generation meets the max generation number, it terminates and the GA ends. And here we have the addition of with the wisdom crowd concept. In our case, I decided to integrate this part after the discard step. And so the wisdom crowd operation begins by selecting a percentage of the top fittest chromosomes. And then it performs crossover between each one of those chromosomes. So it follows the idea of shared, the contribution of many minds is regardless of if the individual are optimized or so-called fittest or not, is still better than selecting the top fittest chromosome and then perform crossover. So next up we have our testing data and our results. So the testing I've done was based on two variations. The population size, which we increase as we perform testing, and the generation size, or the maximum generation number allowed. And each one of these configurations was ran 10 times. So as you see on the right side, we have a table. If you notice the headers, the horizontal headers, 100 over 100, 100 over 150, and so on. What that means is the first column represents 10 runs for configuration size or population size 100, generation size 100. In the second column, 100 over 150 means population size 100 and generation size 150, so on and so forth. And for each one of those rows, it represents the optimal path that was found at the end of each run in terms of total cost. And then at the very bottom, we have the mean, which is the average of those 10 runs for each one of those configurations. And the table above is the GA plus wisdom of crowd, and below that is GA only. And and then to the left of that, at the bottom left corner, we have the execution time for each one of those runs, or the average of 10 runs. And then I'm going to move on to the next slide because that's where I'm going to be doing the analysis, and then I will go switch back and forth between the two slides as I'm discussing the analysis. So the first observation is the solution improved as we increase population size or generation size. So if you notice here, we have, let's just start picking this one. We have population size 100, max generation size 100, and we found an optimal solution of 5,575. And if we move over to the next column, which has an increased generation size of 150, we see an improvement, right? The value increase. And then next one afterward, let's say we go from increasing population size, so let's say 100 to 150 right here, we see, actually a decrease in performance, but that could be any number of reasons. But it's generally, though, when you increase the population size, you typically see better results because you're increasing the diversity of the population, or the chance for more diversity, right? Second observation, GA plus wisdom of crowd performs slightly better than GA only. And if you notice, GA is here, and let's try to match a specific configuration. You notice here, for this configuration, GA plus wisdom of crowd came up with 5,900, versus here it's 5,800, so there's a slight improvement. It's not consistent though, and that may be the result of a couple of things which I will discuss later. However, one thing that was definitely consistent was GA plus wisdom of crowd took significantly longer to execute, as you notice in this graph over here. Regardless of the configurations, you notice that wisdom of crowd the addition of Wisdom of Crowd adds extra time to the execution, which makes sense because GA plus Wisdom of Crowd includes GA, but then also perform an extra step, which is going to take extra time. And here in the conclusion, I've laid out some of the things that, the overall state of the project and how, it could improve. So overall, I believe the algorithm was successful at optimizing the solution. However, I do think that there are rooms for improvements, such as trying different crossover or mutation methods, or just simply testing a larger sample size, or just using different configurations for testing. And that's it. And here are some of my references. Thank you for joining.